Okay, so we just got finished up talking about languages and formal grammars, and in this video we're going to be looking at a particular kind of language, which is the language of mathematics. This video is going to be concerned with the syntax of mathematics. There is no meaning to any of the symbols that we're going to write down. We're just going to talk about the writing of them down. That's kind of the point of today. So, and I say languages, remember, because there's going to be more than one language depending on the types of objects that we're interested in studying. Now, that word object is very loaded, and that's going to have to be its own video to talk about like what it is that we're trying to study in math. But for example, if I'm interested in studying graphs, then I'm going to want a language of graph theory. If I'm interested in studying numbers, then I'm going to need a language of number theory, and so forth. And so there's going to be a slightly different language for each one, but there will be commonalities among all the languages. And so as in terms of the symbols, that amounts to having a few like base symbols. There's like a base language, like a base set of symbols that'll be in every alphabet, and that's really this chunk right here. So what's here? We got, first of all, we're always going to have the logical symbols. So this is what I'm specifying right here, by the way, is the alphabet. I would say that maybe like of what I wrote out, like this chunk is just laying out the alphabet for a language, specifically the language of number theory, but I'll get into that. In any case, what's the alphabet consist of? The alphabet's going to consist of this kind of wedge symbol, this kind of V symbol, and then this this barred symbol. I mentioned before that this meant negation. This meant not. You put it in front of something and you're saying it is not the case that whatever comes after. But again, just, you know, this has no meaning right now. It's just a symbol. Same thing with these two. We're going to put this in between two things, and it's going to mean this thing and this other thing. Same thing with this. It's going to mean this thing or this other thing. But right now, they're just symbols. We have them. Same thing with these quantifiers that we already talked about. We've got this there exists quantifier and a for all quantifier. Now, you can take a minimalist approach and you can say that you only really need one of these, and then you can negate it. You can negate it to get the other. But for some, you know, just I'm striking a compromise here between minimality and ease of explanation, and kind of like a, you know, what would be natural, I guess. Also, you know, parentheses. We're always going to have parentheses, and you can also have whatever else you want. If you want to have commas, you go for it, kid. If you want to have brackets, you go for it. You can add whatever extra kind of like that kind of stuff that you want, but all you really need is parentheses. Okay, so that's it. That is the alphabet. Oh yeah, and then finally we also have variables. Of course, you can't do math and not have variables. I'm denoting this set var, and I'm going to say that it's like, this is like the master set. It's got all of the it's got all your favorites, all the variables that you want. It's got the Greek letters, it's got the English letters, it's got some Hebrew letters if you're going insane. Just all your favorites. Just dump them in a box, call it var. We're going to assume it's finite. You don't have to. You can even assume it's infinite. But for our purposes, I at least got to have you agree with me that whatever your favorite set of variables is, it has to be computably enumerable. If that's too complicated, then you should just settle for it being finite, because it needs to be finite. So I'm going to assume more or less finite set of variables. And again, variables, what I mean here is just symbols that we might use as variables. So this is the stuff. These symbols will always be present in any language of mathematics that you're talking about. Hey, it's me from the future. I just wanted to make sure to note that I did forget one of the symbols here, which is this guy. This is a symbol that will be very important, that we're going to use a lot. And essentially, the idea is that if you put two things on either side, then it's going to mean A implies B, or if A, then B. That's what that's going to mean. So this is a symbol. I should have included it. I forgot it. Technically, it's unnecessary, but it's you know, for the purpose of just, it's an important thing to have. And then specifically, we're also going to always have, and then now we're going to move into kind of like the territory of specific languages of mathematics. And there is something you can say in general about all languages of mathematics, which is that you're always going to have three special types of things. You're going to have function symbols, relation symbols, and constant symbols. These are going to be present in every type. These are always going to be present, or maybe they won't be. Maybe your language won't have constants. But everything else that it will have, all the extra stuff, can amount to one of these three types of things: functions, relations, and constant. Now, I'm going to kind of go through this example of number theory to make things more clear and less abstract as we go through this. And in number theory, in the language of number theory, we have an alphabet consisting of two relation symbols, those relation symbols being less than and equality, and then 4 function symbols, which is the plus function, the times function. This E means exponentiation. You can use a different symbol, but I'm just going to use this. And then this S here, this isn't entirely necessary. This is the successor function. It basically adds +1, right? S of 5 equals 6. These are kind of functions. And so these are just symbols, right? We're calling these two relation symbols. We're calling these function symbols. What's the difference between a relation and a function, though, in principle? The idea here is that if I put two variables on either side of a less than symbol, then what I'm really making is a statement about A and B. I am saying something about A and B's relationship. I'm saying that A is less than B. Same thing with equality, right? If I put two, compare that to putting them on either side of a plus sign. This is not a statement about A and B. This is a number, or a term in a more general sense. This is not a statement about A and B. So we have terms, and then we have statements that we might want to make. No statement is being made for any of the, for putting two variables on either side of these three things. You don't get a statement about them. You just get another number in principle, at least up to interpretation, right? Right now, but that is kind of the difference between relations and functions. In any language of mathematics, you'll have some relations and some functions. Another example would be like the language of set theory. The language of set theory is much simpler. It doesn't have any function symbols. It only has a single relation symbol, and that relation symbol is this guy. There is a member of. A is an element of B. That's another relation symbol. If I put two things on either side of this, then I am making a claim about A and B. So that's, hopefully that makes sense. That's the difference between a function and a relation. In any mathematical language, you're going to have functions, function symbols, relation symbols, and constant symbols in your alphabet. What's the constant symbol? Well, there's many constants. As you know, in principle, there's as many constant symbols for the language of number theory as there are numbers, but we can actually get away with just one. So let's do that. You have many, there's many constants technically, but you can get away with just 0. The rest can be defined, and that's kind of why we have the successor function. If I want 8, if I want 8, or let's say if I want 3, I can just kind of, instead of writing 3, I can write, and we'll see why, again, this itself is like a syntactical thing that I have to explain is like allowed, but in principle we're going to have that what we wanted is 3. 3 won't exist in our language. This is not in our alphabet. This is not in our alphabet. I cannot write. But I don't even want to say equality. This is not in our alphabet, but S of 0. Is that enough? 1, 2, 3. Yep. This will be. This will be a valid term, and it will be, and it is. You can see that it does consist only of symbols. Symbols in our alphabet. So I can represent 3 as this. I can just write this instead of 3. And now I don't have to have infinitely many constant symbols to talk about the natural numbers. I can just talk about 0 as the only constant. You don't necessarily have to do it that way, but it does keep the language of number theory. It does take like kind of the appending of the vocabulary of number theory. It does take the alphabet of number theory, the extra symbols, and only adds a finite number of them to this set here. And then we're still in finite land. Keep in mind, if your set of variables is finite, which I recommended you do, you don't have to, but I recommended it, and you accept that you can just get away with just a constant symbol and a successor function, then we still have a finite alphabet here. We still have a finite alphabet, and we can talk about all the natural numbers. And by talk about, I don't necessarily mean anything yet. I just mean that any statement you might want to make about natural numbers syntactically can be represented with this alphabet. Again, we're starting with the metamath. You can already tell that certain things I'm saying here are getting kind of confusing. Just don't worry too much about it. We're going to get through it. So that's the alphabet. So this is just the pure, listing of symbols. Now let's talk about what is the language. The language is a set of words, right? A language is a set of strings over an alphabet. So we've talked about the alphabet. What's the language? The language of a theory, the elements of the language of a theory, the strings that are valid, they tend to be called well-formed formulas, or WIFs for short. That's what my advisor calls them, WFFs. He just calls them WIFs. I don't know if that's common or not, but I'm going to call them WIFs. So the WIFs are the elements of the language of a mathematical theory. They're generally going to be denoted with Greek letters such as phi or psi, stuff on that side of the alphabet. And so now I'm going to define the formulas. So we're going to define them inductively, and you'll see what I mean by that. It's not as complicated as it sounds. So first we're going to define what are called the terms. I mentioned up here that a plus b is a term, right? Again, a plus b is a number, but we're just talking about syntax. And the idea is that this is to be interpreted as an object rather than a statement. So the terms are the objects. The terms are the things that we syntactically think about as objects. So first of all, every variable on its own is a term. Every constant is a term. So so x, if I just write an x here, and that's a variable, that's a term. If I just write an 8 here, that's also a term. If t is a term, then so is s of t. So I can write an s of x here. I can write an s of 8 here. What I'm saying here is that I can put the successor symbol here, and then I can put my term between two parentheses that are next to the s. That's all I'm saying. I'm not saying anything about s of t. I'm just saying that the things that are allowed are, if I have a term, I can put two parentheses around it and an s in front of it. That's all I'm saying. I'm not saying anything about what this thing actually is. And then if t1 and t2 are terms, then so are t1 plus t2, t1 times t2, and t1 e t2, exponentiation. Again, I can't say this enough times. I say plus, I say times, I say e. All I'm saying is that this is syntactically viable. This is a valid term. And there's also parentheses that are optional. If you want to write t1 plus t2, you can do that. If you want to write t1 plus t2 with parentheses on either side, that's also valid. So that's kind of an addendum to that. So those are the valid terms. Those are the valid things syntactically that we are interpreting as objects, stuff, right? Not statements, but rather stuff. Now we'll define the WIFs, the actual WIFs. So, and again, I'm defining the WIFs for number theory specifically. I should mention that this is specifically WIFs in the language of number theory. I'll explain how you generalize this to WIFs in a general language. It's not complicated. So first of all, notice that all of these are defined in terms of terms. So I've defined what the terms are, and now I'm saying what statements I can make about the terms, right? The terms are the things I want to make statements about, and the WIFs are statements about the terms, kind of. So if T1 and T2 are terms, then so is T1, not so is. If T1 and T2 are terms, then T1 equals T2. I can just put this double bar sign thing here in between the T1 and the T2, and that counts as a WIF. Same thing with putting this caret thing in between the T1 and the T2. These are both WIFs. What I would do to generalize that is I would say, like, if R is a relation, more general, if R is a relation symbol, and I kind of lied about saying that's all there is. You also have to specify on two variables. There's kind of like an arity function where you kind of have to specify like what, maybe your relation takes 3 terms. Maybe your relation takes 4 terms. But if R is a relation symbol, then, T1 R T2 is a WIF. I'm just always allowed to do this with any when I have a relation symbol, I can take the appropriate number of terms and arrange them in the appropriate way, and I'll have a WIF. And these particular ones that you make just directly out of the relation symbol and to some number of terms, these are called the atomic relations. It's not super important. None of this is really important for that matter. I should maybe specify this. I'm listing off this kind of complicated language of mathematics, but it's not super important that we do so. It's only important that I make a point with it and that you can kind of have a vague idea of what it is I'm writing down when I write down arbitrary formulas. We're not going to really do anything with this. We just want to be able to talk about it. So if phi1 and phi2 are well-formed formulas, then so are phi1 or phi2 and phi1 and phi2. So I can put this or symbol and this and symbol in between any two well-formed formulas and have another well-formed formula. And again, parentheses are still optional. And then finally, if I have a single single well-formed formula phi, then for any variable symbol x, I can put a there exists sign. I can put this backwards e, and then an x here, and then the well-formed formula inside of here. And that this well-formed formula may or may not involve x in some way. Probably will, but it doesn't have to. And then also for this upside down a is also allowed. And that's it. That defines, that gives you a full definition of all of the WIFs in a language, or all the well-formed formulas. So what would change also respect to a more general theory, or a more general field of mathematics, is that, right here what I have, with these two, basically, I have 4 function symbols, right? I have plus, times, exponentiation, and this s thing. This s thing has arity 1. So I had to kind of say t1 is a term, t is a single term, so is s of t, because s kind of in principle only takes one input. These guys all take 2, and so I can arrange them in the appropriate way. If I had function symbols, it's entirely possible that I have function symbols involving 3 things, right? I could have maybe a to the b to the c or something, right? Maybe I want this to be a function, and so then, like, if this is like a function symbol that I want in my language, I would have to kind of say, this is a valid a, e, b, e, c. I mean, that's a bad example because I can make that out of 2 other functions. But generally, you're going to have some number of expected terms to your thing you're talking about. And just, plugging those things into the function symbol is always going to be valid. This is, as you're already noticing, this is kind of hard to talk about. And we're not even into anything yet. So here's some examples of well-formed formulas in the language of number theory. We're gonna more and more stick to number theory as we go through these videos. Number theory is going to become more and more important to us. So here's some example of well-formed formulas in the language of number theory. First of all, y equals, and again, phi is the WIF, right? This is the well-formed formula. I'm talking about it. So I'm tempted to use this equal sign here, right? But this equal sign is an equal sign in the metamathematics. This is in my world. This equal sign exists in my world. This equal sign is just an abstract symbol. This has a different meaning than this. Sometimes people use like a wavy equal sign to distinguish one from the other, but they kind of mean different things. This is a well-formed formula that equals a string, but the string itself involves an equal sign. So that, this is an equal sign in the metamath, and this is a symbol. Anyway, this is a valid well-formed formula. Let's kind of make sure that we understand that. So let's say y equals x1 plus x2 plus 8. And when I write 8, by the way, what I really mean is this garbage here. But don't worry about it. I'll just write 8, and we'll know what we're talking about. Why is this a well-formed formula? Well, because this is a WIF, because t1 equals y and t2 equals x1 plus x2 plus 8 are both terms. Specifically, t2 is a term, because x1 plus x2 is a term. I don't even need to put parentheses. Is a term. Why is this a term? Well, okay, I'll say t2 is a term because x1 and x2 are terms. X1 and x2 are terms because they're variables. They're variable symbols. And we said that any variable symbol is a term. And then 8 is a term because, right, because 0 is a term, because all the constant symbols I said are terms. And so s of 0 is a term. I said that I could always do that. And so s of 0 is a term, and so s of 0 is a term, all the way up to 8. So I've confirmed that x1 plus x2 are terms. 8 is also a term. And so x1 plus x2, that term plus 8 itself is a term. And so this whole thing is a term. And so I have two terms put on either side of an equal sign, and so that's valid. So t1 equals t2 is a term, is kind of an atomic formula. An atomic well-formed formula. This is very kind of strange. It might seem strange that I'm checking this carefully, that this is a well-formed formula. The reason I'm doing that is because I wanted to kind of demonstrate, and I think I did it badly, but I think I did it, that the confirmation that this is a well-formed formula happens mechanically. It happens via this burrowing process. I kind of look at like the outer form of this thing, right? What do I have as the outer form? I have this thing and this thing with an equal sign. Okay, so then this is a term. This is a well-formed formula if and only if these two things are both valid terms, and so I have to check that these are both terms. Okay, this is a term, obviously, because it's a variable symbol. This is a term, and I have to kind of go there. I have to kind of look at the arbitrary form of this term, right? The form of this term is this thing plus this. And so I have to kind of check, is this a term, and is this a term? And if these two terms, then this is a term, and then I can say yes. So you can imagine algorithmatizing this. You know, it's easy to check it yourself, just kind of by sight, right? It's easy to check it, but I can also make an algorithm out of it to teach someone else how to check it. And as Turing says, that's the most important part. So here's some other examples. X less than y, that's obviously, you know, a well-formed formula. And then here's a more complicated, here's a more complicated one, like psi is equal to, and again, this equals in the metamathematics, there exists an x such that for all y, x is less than y, right? This is a valid thing because this right here, x less than y, that is a well-formed formula. We've said it right here. Putting parentheses around it is also a well-formed formula. We said that. And then putting the for all y, x less than y, that, you know, you're always allowed to slap the for all y in front of it. So that's valid. So this whole thing is a well-formed formula. And then I also said that for any well-formed formula, I can slap the there exists onto it, and then I still have a well-formed formula. And so that confirms that this is a formula. So again, you can kind of, you're getting vibes of this like kind of burrowing down algorithm for checking to see that these things are well-formed formulas. So the conclusion is that it is easy to check, given a string, whether or not it is a well-formed formula. And that is significant. Why is that significant? That's significant because, therefore, it's easy to check. Let me write that again. Let me write that again. Yeah. Let me just say it's easy to check algorithmically on paper that a well-formed formula, that a string is a well-formed formula, or is not a well-formed formula. That is to say, a string in the language of number theory. It's easy to check that. What are we going to say next? Therefore, by the Church-Turing thesis, this language is computably enumerable. So we can think of, so what's the significance of that for us? The significance of that for us is that we can imagine there exists a machine. So let me make this even more clear. I.e., there exists a machine which will list out every whiff, one by one. So we can always kind of imagine doing that. We can run through a check of every. We can kind of, just like we made a lot of useful algorithms out of just the kind of concept of going through all the strings one at a time, right? Now we can do that with the well-formed formulas. Another thing we can say, also, this confirms that this language is given by a formal grammar, is generated by a formal grammar. It's generated by a formal grammar because there's obviously a Turing machine that computably enumerates it, so it has to be a formal grammar because we said those are equivalent statements. And I didn't define these things as formal grammars. It's actually probably harder to do it. This is kind of an inductive definition, but it is a definition, and it's a definition that you can use to check if a string is a whiff, and because of that, there's a computer that does it, and because there's a computer that does it, it has to be generated by formal grammar. So I just proved by the Church-Turing thesis that this is a formal grammar, despite me not defining it as that. So any language of mathematics is generated by a formal grammar. Any language of mathematics is computably enumerable by the Church-Turing thesis. These are all equivalent ways to say the same thing. So that's pretty much, well, okay, that's not all we need to say about the syntax. There's a couple things we want to say still, but that'll be in the context of the next major discussion. We've talked about the syntax of mathematics enough on its own. It is time to move on to talking about the objects of study in mathematics.